Today's mini lecture is on the origins and the importance of the Earth's magnetic field. Now, the magnetic field is commonly depicted as a dipole, and you've heard that word before. You know that a dipole magnet means that there is one end that is positively attracting and the other end negatively. And it's a decent approximation of the Earth's magnetic field. You can see this diagram here showing the magnetic field lines with the magnetic field lines entering at the north magnetic pole and exiting at the south magnetic pole and forming these big wide arcs around the Earth. Note that the rotational axis and the magnetic pole are off by about 11 degrees, and that varies from place to place around the Earth a little bit. We call that difference between magnetic north and true north declination. And if you're ever being very careful with the map, you need to know what the declination is in your area. So why do we have a magnetic field? Well, the Earth's outer core is liquid, and convection occurs because inside that liquid it is hotter at the boundary to the inner core than it is at the boundary to the mantle, and so the liquid moves by convective currents within the core. Now, it is mostly made of iron, and iron is a very good electrical conductor, and so as the core material moves, it generates an electric current, which generates a magnetic field. Remember that from physics, right? This is how electromagnets work, that a moving electrical current creates a magnetic field. Geoscientists use this for a lot of very interesting projects, one of which is to tell where continents were in the past. And we'll see that when we start to look at plate tectonics and the shape of the Earth over the years, that the continents have moved. The reason that we know that is that we can tell from a particular rock in a particular place where magnetic north was at the time that rock formed. And of course, we know that the North Pole doesn't move, so if the magnetic north is pointing to somewhere other than the North Pole, then the continent itself has to have moved. So this is a picture of a guy collecting coring data from a rock outcrop in order to determine the paleomagnetism of this particular rock. Now, we can use a supercomputer to model what the magnetic field looks like as it is generated in the core. And this is a picture of a supercomputer model. You're going to do a reading about this, so you'll get to learn a little bit more about it. This is very complex, as you can see. Not quite as simple as a dipole magnet. And this happens to be a relatively stable period in the magnetic field of the Earth. And so you can see the blue field lines and the orange field lines are generally behaving themselves and going where they're supposed to go, while there's a lot of chaos in the middle. We do know that the magnetic field reverses from time to time, and during that reversal, the magnetic pole lines in the model become substantially more complex. But let's just look for a minute about what I mean by reversal. So we are in a period right now of normal polarity, as you can see at the top, where our compass points towards the north, which is the magnetic North Pole, field lines going in at the north and out at the south. But there have been times in the past where the opposite was true, where the field lines go in at the south and out at the north, and that we call a reversal. Over geologic time, there have been many reversals, and we can see them on the ocean floor. That's the best place to record them because we're constantly producing new crust at the ocean floor, and we're producing it out of basalt, which has magnetic minerals in it, and so those magnetic minerals line up with their magnetic field directions either pointing towards the north or towards the south. This is a sketch of that showing the current rock in the middle in a darker red, and then as you step away symmetrically on either side, orange and lighter orange, and those are just earlier stages of rock, and then in between white, and that indicates reversed polarity when the magnetic field was pointing south. Now, it's a good thing we have a magnetic field because it helps protect Earth from harmful radiation. The highly charged protons and electrons called the solar wind are deflected by the magnetic field around the Earth, and it really is what makes life on Earth possible. If we had that much solar radiation hitting the Earth, then DNA would be badly damaged and life probably would not have formed. certainly not as we know it. So we're happy for the magnetic field. It's a good thing to have, and we're very interested to see what happens during a reversal and whether that dangerous solar radiation would hit Earth during a reversal. Big and important questions.